So the major part that we're covering here will be the link between your geometric series and the financial math or the real life application. So when you look at the first thing that we get on the geometric sequence, and probably one of the base formula that we have been doing is the compound interest formula. So now let us say that there is a quantity whose starting value is P, and then I'm linking it up like principal amount that we deposited in a bank account or something. So let's say an account amount is P, it increases with R percent of rate, and R percent of rate, like, every week or every year or every day, the way we say. But now if I look at here as a compound interest formula, and let us say that N is the number of years that this money is in, R percent is, let's say, compound interest formula. So when you find out the total amount that will be in the bank account is going to be, suppose you deposited P, it'll be 1 plus R upon 100 to the power N after N complete years. After N complete years. Now, if I take this as 1 plus R over 100 as like a, let's say, capital R, or the ratio, you will be able to see that this amount is actually following a geometric series. So after first year, A1, if I find out, it is P times R to the power 1. After A2, it'll be P times R square, and so on. So actually, when you look at this formula itself is a geometric sequence. So a lot of times we use the logic and the general idea to get the kind of questions that IB expects on you or using this formula. Now, let me just give an example. First one is that, let us say the initial population of rabbits on a farm was 50. The population increased 70%, 7% each week. How many rabbits were present after 15 weeks? So when you look at after 15 weeks, since it is like each week they're increasing, so like the rate of, like, if I compare with this formula, the rate of interest is the 7%. So here what we have is the final, like, you can say A15 is gonna be 50 times 1 plus 7 over 100 to the power of 15. So A15 will be 50, 1 plus 7 over 100 to the power 50. Similarly, if I wanted to find out what will be the amount after 30 weeks, or how many rabbits will be present after 30 weeks, it will be 30 times 1 plus 7 over 100 to the power 30. Now, mind you, here there is no n minus 1 formula. It's like first term into ratio to the power n minus 1. Lots of times students make mistake, because the only difference is that why we put, like, when you put n minus 1, so this can be n minus 1. If suppose I am calculating interest at the beginning of the year. Now, when I say complete n years, means you're going to get interest on even the amount that you deposit this year. So it is really important to calculate. I'm going to show some questions explicitly on compound interest after this, but this is something which needs to be discussed carefully. Okay, the next question is, how long will it take for the population to reach to 500? Now, this is like a little bit of technology based question. So here, as we can see, that it grows according to the model 1 plus 7 upon 100 to the power n, and this should be equals to 500. So this will become 1.07 to the power n is nothing but 10. And then you solve for n. So when you solve for n using either n solve that you can see on a calculator, solver, whatever it is, you get the answer as somewhere around 34.03. So around after 34 weeks, approximately, your population will reach to 500. Now, this is like a general presumed knowledge-based financial calculation, or you can say real life calculation. Now, what I'm going to focus on is, from here onwards, will be purely focusing on the compound interest and its application. So let us just, before I go to that part, I'll just say that obviously you could use graphical method as well. You could plot the graph of 1.07 to the power n, and you draw y equals to 10 line and take the corresponding value, which is 34.04 something. And then that can be taken as the final answer. So you can use graphical method or calculator to solve this particular question. Now, when you're looking at the compound interest formula, now explicitly the compound interest formula, let us say if you invest, I'll just share the screen here. So let us say, for example, if I invest an amount of P at a rate of interest R% compounded annually and for n years. So as we know, the compound interest, as I just discussed, given by P, 1 plus R over 100 to the power n. Some textbooks you'll see this is T, and that's what it is. So we'll begin up with the basic part first. So let us say I deposited $5,000. I'm not going to do calculations to save time. It's 5,000 and rate of interest is, let's say, 12% per year. And you deposit this amount after, let's say, n years, let's say for 5 years and as 5 years. And I wanted to find out how much is the money in the bank after these 5 years, these 5 complete years. So now when you look at this formula, now see here, you're not making any intermediate deposit. Remember that you're not making any deposit in between. So the value of this will be 5,000 into 1 plus rate is basically 12 upon 100 to the power of 5. This is the amount when you compound yearly. So I'm not calculating what's the exact value of this. I'll probably do towards the end. 5,000 times 1 plus 12 upon 100 to the power 5. This is the amount in the bank account if you compound this interest yearly. Second, what if you compound this amount semi-yearly? Like if you compound in a year, let's say the money grows, whatever money has grown, then you again compound on that within half a year itself. So when you increase the compounding numbers in a year, your formula modifies a little bit. I would put in this way. So the total amount when you compound, let's say k times in a year, this is my custom formula, k times in a year. So in that case, it will be principal 1 plus rate upon 100k to the power of k times n. Let us take an example. What if the same amount has been compounded semi-yearly? Semi-yearly means in a year you're compounding twice. So the amount that you'll get will be 5,000 in bracket 1 plus 12 upon 200 to the power of 5 times 2. So this will be the amount in the bank account after 5 years itself, but twice twice a year compounding. This is like semi-yearly compounding. Next one is what if the compounding is quarterly? So each quarter, in a year there are 4 quarters, so like you'll compound 4 times. So the k value is 4 here. So amount will be 5,000 1 plus 12 upon this will become 400 to the power of 5 times 4. The logic is that you will have 5 times 4 because 20 quarters in a year, in 5 years. And also the rate of interest become 1/4 because if the entire year you're getting 12%, for 1 quarter, the rate of interest is 4%. I mean 3%, 12 upon 4. So that's why we're dividing by 400 instead of 100. So what if I'm doing, let's say, monthly compounding, like in a year, if I'm compounding every month. So the amount is going to be 5,000 1 plus 12 upon this is going to be, let's say, 400 here. So if I compound yearly, if I compound monthly, so it'll be 1 plus 12 upon 1200 to the power of 5 times 12, because in 5 years we'll have 60 compounding periods. So if we calculate these values, exactly, you're going to get the total amount accumulated under each condition of compounding. So this is how you compound using the manual formula. This is using the GDC is different, like there are shortcuts to do in GDC, which I'll be covering up in next class. But at least for now, this is the basic backbone of compound interest presumed knowledge. So now what we are doing next is the continuous deposit in an account. Now you learned about compound interest. Now what we'll be learning is, what if we deposit the amount continuously in a bank account? So generally this kind of deposits are periodic. So you, let's say, for example, I'll give an instance is, the key term that we are using here is superannuation, and the instance that I'm giving for this is, let's say, as a particular, like, careful parent, I decide to invest $100 every month, every year, in bank account at 12% compounded interest without any withdrawal or without any kind of like further, like, sub funds. Like, I'm just taking $1,000 and I'm depositing every year, and I'm going to find out how much will be the worth of my investment after 20 years. Or you can say, how much will be the money in the bank account after 20 years. So when you're talking about the continuous deposit, like this kind of questions are referred in like superannuation, you'll not find this keyword in the guide. But when you're looking at the continuous deposit, this is one of the kind of questions like more or less applied on sequences, compounds interest format, but multiple deposits. So let me just start. Let me explain you the story, what is happening out here. So suppose that you started with $1,000 in a bank account today, which is like your first birthday. This is your first birthday. After second birthday, so like now this money is in the bank account for first year and second year, but at the beginning of second year you deposit another 1,000. So on this money, now this and this money lies in bank account for another like 2 years, and then obviously at the beginning of the third year you deposit another $1,000. So I want to find out how much is the total money in the bank account. So here what we're going to do is understand that for what period each money, don't consider this as a single investment, consider them as 20 different investments and 20 different values of the money. Suppose I invested $1,000 today in a bank account, and that money is lying for 20 odd years. I'm not looking at it at all. Of course, that money is going to give me 20 complete years of interest. And so the money that I deposited 20 years ago, I would just like to read the question, that a woman invests $1,000 at the beginning of each year under superannuation. As I explained it to you, superannuation is like you deposit at the beginning of each year, or without any like removal, or without any further addition of sub funds. If the interest is paid at rate of 12% per annum, compounded annually, how much is the worth of investment after 20 years? This keyword becomes essential between your understanding of this geometric series and the correct answer that you get. Lots of times students think, okay, this money is in the bank account for 20 years, so it'll be formalize, okay, 1,000 times will become, they apply geometric series formula, unfortunately, sometimes, I don't know how. So if this money was lying in the bank for 20 exact complete years, it will get, or it will gain me the value of 1,000 times 1.12 to the power 20. So this will be the worth of the investment that I deposited 20 years back. Coming back now to the one deposit that I made on the 19th year. Today, I just, let's say, completed like 20 years of my investment. It is the end of 20th year. And I used to deposit, let's say, on the 1st January. and I'm calculating the interest at the end of December. So my money that I deposited 19 years ago will give me complete interest of 19 years. And the worth of that investment is going to be this. So 1000, 1 plus 12 upon 100 to the power 90. Similarly, the money that was in the bank for 18 years completely will give me this much of worth. So remember that these are the money that invested 20 years ago. This was 19 years ago. This was 18 years ago. And the money that you just invested at the beginning of 20th year, this year, will give you 1 year of interest. And that's what will be its worth. And of course, to get the total net worth, you're going to add these amounts, okay? You're going to add these values. So when you add them, you get the net series value, which will be the worth of the investment. So let us say if you look at this forms proper geometric series, okay? So it forms a proper geometric series. Now here, my series, they have written like with the decreasing power ratio. What I would do is, even if I write down with this as 1000, it'll be 1.12 plus 1.12 square and so on, and 1.12 to the power of 20. And this forms a geometric series. So you can find out using your formula. So which is going to be 1000. U1, 1000 is as it is. U1 is 1.12. Ratio is 1.12 again. So 1 minus R, which is 1.12 to the power of 20 upon 1 minus 1.12. And this amount comes to 80,698.74. So this is going to be the worth of the net investment after 20 years. Yeah, so there's a printing error here. So actually the first investment, this we are getting 1.12 because of, let's say, 1000, 1 plus 12 upon 100 to the power of 20. So this becomes 1.12, which is like kind of ratio of your sequence as well. So this is the general idea about the superannuation kind of problems, where each of the investment is worth looking at as individual investment rather than like a single problem or single investment in the problem itself. So when you're looking at this particular problem, if the interest was, if the calculation of the compounding or final answer was done, here you can see that at the beginning of 20 years, what will be the worth of investment, not after 20 years, the moment you make 20th deposit. So today is the 20th birthday of yours or your kid or whatever it is. You go and deposit the money. On that money, you're not going to get any interest for the year, because you're depositing today. You can't expect interest for that money. So that will be in the bank for just, it'll be like $1,000. The one you deposited 20 years ago now will not get an interest of complete 20 years. It will just get an interest of 19 years. Because remember that you're making the deposit at the beginning of the year and you're calculating the interest also at the beginning of the year. So the one you deposited at the beginning of 20th year, and today I just completed 20. So in short, I mean that before I just go on to make the 20th deposit, it would be complete 19 years. So that money, now the sequence in that case changes a little bit, and the last investment that you did will be worth only for 19 years. So this is something that you need to focus why it is after, and if the interest is compounded at the beginning or at the end of the year, this does matter on into the problems like this. So when you are solving a problem, be very careful while you're reading it, and make sure that you try to decode the problem into several subsegments and then try to attempt it. So this will be the one of the example of superannuation. And let's now go to the next part, that is the loans and annuities.